All right, so organometallics. So far, we've only talked about them reacting with ketones and aldehydes, but they are really strong nucleophiles, so they should really react with anything that's electrophilic. So that brings up, well, what other electrophiles have we seen before? And one electrophile that we've seen is an epoxide. Epoxides are those three-membered rings, a lot of ring strain that allows them to open up. One type of reaction that we've done with them this semester is taking the acetylide ion and reacting them with the epoxides. And I always want to relate our new material to our old material. So take a minute, pause the video, predict the product here. We have our acetylide ion, it's already formed, we don't even have to deprotonate it. We have our epoxide, what is that going to form? All right, you paused for a minute, you did it. That acetylide ion is negatively charged. Both carbons there are partially positively charged because they are attached to that oxygen, but this one is less sterically hindered, so that acetylide ion is going to add to that more sterically accessible position. So the mechanistic arrows that we could draw would be that going there, and that would provide a product that looked like this, where essentially we have the alkoxide that is just a single stereoisomer there because we started with the, just covering up that light so you see the triple bond there. So count your carbons, compare them to what I have here. Make sure you've added the right number of carbons. What about your stereochemistry? This would be 1, 2, 3. This is S. This is an S stereocenter. Make sure yours is S. You could have drawn it in a different way. We have to remember that we have to figure out what the product is in any orientation that we could draw it in, and you could make a mistake how you're drawing it. So make sure that you're on the right page there. What about the second one? Go ahead and pause the video and predict the product here. What would you expect an organometallic to do? This, I just have an M there. What I mean is that it could be an organolithiate. It could be a grignard, right? M kind of stands for either of those metals. So predict the product. Boop. All right, you did that. You also noticed that I left off a positive charge here. Good catch. But organolithiates, organometallics, they're going to react the same way that our acetylide ions do. They should, right? This is essentially a negatively charged carbon with a positively charged anion there, just like this one looks. So it's going to add to that more sterically accessible side, as anions typically do. One thing that's a little bit different here is that we have two reagents. Hopefully you took note of that when you predicted the product. The first addition would have made this. We have the 2 carbons from our organometallic and then the 3 carbons of our epoxide. Again, we have the S stereochemistry here. Make sure yours is also S. And then secondly, we are doing an acid-base reaction. So we're just protonating our alkoxide intermediate here. So what's the product look like? It's an alcohol. So epoxides are a great way to extend a carbon chain by having it react in that way. So epoxides are something that reacts as an electrophile with these strong nucleophiles, these organometallic reagents. We're going to talk about another electrophile right now. All right, before we get into this new electrophile, I just wanted to mention on your course packet, we talked about the epoxides, but I didn't hit that bottom statement. Anionic epoxide openings occur at the blank substituted position. Hopefully you can fill that in based on what we talked about, but it is the, wait for it, the less substituted position. That should Makes sense based on what we just did. And these organometallics can also add to carbon dioxide. So let's have you guys try and predict the product here. And start that out by drawing what the Lewis structures of carbon dioxide is. These organometallics, they are nucleophiles. Where is their negative? Well, where are they going to add to CO2? Think about that and then try to predict the product. If you do it without me telling you, you're going to remember it a lot better. All right, you've done that. So CO2, it's got, the oxygens have 6 electrons, 6 valence electrons. Carbon has 4, so that's 6, 12, 16 valence electrons. So we'd have our C, double bond to O, double bond to O, octet, octet, 2, 4, 6, 8, 10, 12, 14, 16 valence electrons. This is the structure of CO2. So now that we have that, if you hadn't already predicted the product, predict the product now. All right. You did that if you hadn't already done it. So how is an organometallic going to react with this? Where's the partial positive? Where's the partial negative? We have the partial negative right there. We have these oxygens are more electronegative than the center carbon. That means there's a big partial positive right there. That's going to add there. And one of these pi bonds on either side are going to open up as a result. So that would produce our 2 carbons from our organometallic bonded to a 3rd carbon, that carbon, which is now a carboxylate. It has been opened. The CO2 is now carboxylate. So at this point, we have to protonate that to make it neutral so that we can isolate it. We just did that with our standard H3O+. H3O+ has a pKa of what? Yes, negative 1.7. So even though the product carboxylic acid is moderately acidic, it's not as acidic as hydronium ion. A carboxylic acid has what pKa? Yep, a pKa of 5. So this is a lot more acidic than the product, so it would be favored in that forward direction. So again, you guys should be doing your reaction sheets. Now you have a lot of ways of making alcohols by adding organometallics to ketones and aldehydes. You can also make alcohols by adding those organometallics to epoxides like we just talked about. Something that we don't have a ton of ways of making is carboxylic acids. This is a new way of making carboxylic acids. We don't have a ton of ways of doing that, so it would be a short reaction sheet. So yeah, another cool reaction that we can do with these organometallics.